Hello and welcome to another lecture for ECE 205. This lecture we're going to try something new to see how well it works, and I'll try it for the next 3 lectures and then kind of pick the class's mind on which one they prefer. But we're going to try to do everything in OneNote instead of doing lecture slides, and we'll see how that works out in comparison to doing the lecture slides. If it turns out that it's a better format for this course, then we'll do that. And if it turns out that it isn't, it's good little experiment. We can go back to doing the kind of more traditional lecture slide / writing math out type thing. Okay, and also before we begin, one comment that I've received from a couple students on the survey is that I should stop spending a lot of time on the theory stuff. You will be tested on some of the theory stuff, and in general, the methods that we're giving you sometimes break down and you need to go back to the theory to find a solution. So for this course, the theory is very critical for your understanding for being able to solve these, differential equations in general, outside of the handful of honestly kind of very rare examples where the formal theorems that we have will actually apply directly. So I'll still have to cover the theory stuff, but I'll make a few tweaks in the amount of theory versus examples, or at least try to. Okay, so let's get into our new lecture. So in the last lecture, we ended by talking about that linear wave equation and kind of working towards a solution, but we didn't quite get there, and we can make a little bit more progress on that problem. So let's start by continuing where we left off and kind of finish the problem, so to speak. We won't make it all the way to actually solving it, but you'll see what I mean. Okay, so first recall our attempt to solve the initial value boundary problem for the linear wave equation. So what did we have? Well, we had a PDE, this guy here, just UTT, is equal to c squared uxx. In addition to this, we had initial conditions and boundary conditions. So for our initial conditions, we had two things. One, u evaluated at x comma t was just given by some function that we called f of x here. And finally, the second initial condition was that the time derivative of this, and this should be a 0 here, the time derivative of u evaluated at x comma 0 is just some other function g of x. Okay. In addition to this, we gave some boundary conditions. So what were our boundary conditions? Well, we were considering the Neumann problem, so Neumann boundary conditions here, that u of 0 comma t was simply going to be equal to 0, and this was going to be the same thing as u of L comma t, where L is just the length of the rubber band or whatever we're modeling using the wave equation to model. Okay, so from here, previously, we assumed that our solution, so we assumed that our u of x comma t was separable. That is to say, we assumed that it could be written in this form here. Again, this is an assumption. I'm not guaranteed that this will work, but that's what we assumed. Okay, and when we made this assumption, we ended up finding out something about our solutions. Namely, by taking this assumption, putting it in the differential equation, and then separating out the equation that we had into two equations and applying the boundary conditions, we found that x of x was simply equal to some constant times cosine of this n pi x over L, where c is just some arbitrary constant. And then from here, we found that our equation for this t needs to satisfy this differential equation here, that t double prime has to be equal to negative lambda squared, where that's just going to be our negative n squared pi squared over L squared times c squared times capital T. Okay? So previously we didn't solve this equation, and we didn't apply the initial conditions. So let's now solve this equation and then see what happens when we try to apply the initial conditions for this case. Okay, so here, this equation can simply be written as, I could add this term over, so let's do that real quick. Okay, so this equation, if we just look at it for any time at all, we can notice that, hey, this term here in front of the t is just a constant, so we actually know how to solve these problems. If you don't, then just go back and review it. But the general solution to this will simply be capital T of t is equal to some arbitrary constant times sine of the square root of this term times t, so n pi divided by LC t, plus cosine of the same thing, like so. Okay, so now that we have what t of t needs to be, ignoring the initial conditions, which we'll talk about later, I can combine this stuff for x and the thing for t together, and I can find that thus u of x comma t, if it is of this form and it does solve the differential equation, then it needs to be of the form this thing times these terms here. So here I'm just going to write this as c1 sine of this plus c2 cos of this times this term here and drop the arbitrary constant c, simply because it can be absorbed in the c1 or c2. So let's just do this real quick. Okay, so again, I just took t, multiplied it by x, and suppressed this extra constant c, and basically redefined c1 to be c1 times c. Okay, so now that we have this solution, this thing satisfies some of the conditions, but not all of them. One, it satisfies the PDE, and it satisfies the boundary conditions, but it does not satisfy these initial conditions. So let's try to make this satisfy the initial conditions, and we'll see where the problem comes into play. So for the first initial condition, I want that arbitrary function that I don't know, but it was given to me, f of x, to be equal to u of x comma 0. Okay, so if I just plug in 0 in here for t, the sine term goes away, and I'm left with c2 times this cosine of stuff, which that just goes to 0 when I or 1 when I plug in 0, and this cosine term here. So it's just going to be c2 cosine of n pi x over L. So here's where the problem lies. This function f is arbitrary, but I have that it somehow has to be equal to a function of this form, and the only thing I can do here is change the constant c1, or potentially this free parameter n, where n's just some integer, right? So the issue is that unless this f is of this form, then I can't actually get a solution to the differential equation with what we currently have. Again, we will address this later. And yeah, so now let's look at what the other initial condition tells us to get kind of a broader picture of the other issue we need to contend with. Well, the other initial condition was just that this g of x is equal to the t derivative of u, so just chasing that out here real quick. And here I'd have that this arbitrary function g of x has to be equal to something of this form, where again I can only change c1 and n, and yeah, so I have this same issue here. So I could draw this arrow going this way. Okay, so if it turns out that these functions f and g satisfy these conditions here for some value of c1, c2, and n, then all I have to do is pick those values of c1, c2, and n, and then just plug them into this expression up here, and then I get a solution. But if that's not true, then I have to do something else. And while you may think I have to go completely back to the kind of starting point up here and say, well, this possibly can't be true, that u of x comma t is equal to something of this form, it turns out, and you'll see why later, that we can actually solve these equations here with a few extra assumptions on these functions f and g, and using the fact that this is a linear equation. But we'll talk about that after the midterm. Okay, so now that we've kind of addressed how to solve these type of questions, and you will be asked to solve a simpler type of partial differential equation with a particular initial condition where you can actually solve it using this method on the assignment, let's switch over and start talking about spring problems. Okay, so let's put a new header here and jump into it. Okay, so here is a picture taken from your text, and the purpose of the next few minutes of this lecture are to derive the equations that would model a spring oscillating back and forth. And we're going to find these equations by using a little bit of physics that will just kind of taken as given to us and thinking about the different forces acting on the spring here. Okay, so recall a very important law of motion that you probably know from physics is F is simply equal to ma. Okay, so A, if I call the, say, position of the spring as a function of time y of t, this A will simply be y double prime of t. Okay, t. What is m? Well, m will be the mass of the object that we're moving, and within this context, we're going to call the mass of this blob here m. Okay, so m is just the mass of this, and F, that's just the sum of all of the forces acting on this blob. Okay, so this begs the question, what are the forces acting on this blob here? Okay, so the first force is pretty easy to do, so we can split F up. So the first force would just be gravity, right? This thing has a mass of m, and in this configuration, gravity will be wanting to try to pull it down. So we have this force of gravity would just be equal to minus m times the constant of gravity, assuming that we are in a situation where we can assume gravity is constant. Okay, so just cleaning that up a little bit here, we have this gravity force. What's next? Well, what do we know about springs? If you've ever taken a spring and tried to stretch it or compress it beyond its kind of normal length, then you know that it takes energy or a force to either stretch it or compress it. So a string, just kind of denoted here, or a spring denoted here, has its kind of natural length here at this point L. So this is when I just kind of hang the mass and just let it stay there. We call this thing the equilibrium length. Okay, so this thing's my equilibrium length, and beyond that, if I actually compress or stretch this thing by some amount, say delta L, or negative delta L here, then that induces a force. So the next thing I need to do is know how to quantify this force. So explicitly, if I write it here, we have the force from stretching or compressing the string, and this force is given by Hooke's law. So what is Hooke's law? For this class, we're just taking it as a given, since we're not really going to drive it, but the basic idea is that this force from either stretching or compressing the string will be some constant that we don't know, but you can approximate it by actually stretching or compressing the string at fixed distance and finding out how much force it takes, but some constant times the amount that we stretch it by. So we'll call that delta L. So here, again, this thing is a constant, and this capital delta L is the amount that I'm stretching or compressing it by. Okay, so again, just kind of some of the background behind the validity of this assumption here for Hooke's law to hold. We're really assuming that we're only moving the spring by kind of small amounts. If you stretch the spring too much, then this law kind of breaks down. So just to kind of tie that in on the side real quick, if you imagine taking a spring like this and stretching out till it's perfectly straight, if I stretch the spring out beyond here, it's no longer really going to have this constant elasticity, and eventually it's going to break, and kind of the physics of this problem breaks down. But assuming that the spring is moving by a small amount, this holds here. Okay, so next up, this delta L is actually slightly complicated, so let's break this down into kind of its subcomponents over here and think about how we can talk about this delta L potentially in terms of a total displacement here, which is what we actually want to find in this case. Okay, so given an arbitrary spring, there's kind of a natural length to the spring, and let's just call this natural length L. Okay, so this is the natural length of the spring. And at this length, there's no forces on the string, and my displacement's 0 kind of from my natural equilibrium. Okay, so now the next thing I could do is if I take the same spring and attach some mass to it down here, m, this will increase my length from this natural length of L to some new length, let's just say L plus delta little l, okay? And this is a new equilibrium length, and we'll talk about why we kind of want to think about this length first in a second. So beyond here, we can talk about further displacements that would be caused by some external factor, say we pull on it or the wind blows or something like that. And here we would have our natural little spring here, where this is maybe a little bit further down with our mass m. We would again have this L factor here, and then we would have this natural delta L factor, and this delta little l again is just caused by the weight of the mass pulling on the spring, and we can have this extra factor here that we're going to call minus y. Why minus y? Well, it turns out that it's just convenient to do it that way with our definition of distance. So in total, the total deviation from its initial position, delta capital L, will simply be the sum of these differences here. So why is it useful to take the capital L and break it down into these kind of subcomponents? Well, here, the total forces of the spring acting on this thing is just going to be 0, okay? This is coming from the assumption that the spring has no mass, or the mass of the spring is much, much smaller than the mass of the object, which is a fairly decent assumption to use here, okay? So in this situation over here, the force acting on the spring will just simply be the forces from this delta L component. So in this case, these will simply be K times delta L. And this force here is trying to restore the mass back to its original position. Okay, so just cleaning that up a little bit. Then in this last case over here, what is our force? Well, the force acting on the spring, again, will just be K times the total displacement. In this case, that's just capital delta L. And this thing would simply be K times the sum here. So K little delta L minus Y, or simply, if I expand this out, K delta L minus KY. Okay, so here my ultimate goal for doing all of this was to find the forces as a function of only this y function so I can get a differential equation. But here I still have this K delta L term sitting here. So how do we get rid of it? Well, let's clean this up and then talk about that. Okay, so I don't necessarily know what this delta L is, but I know something about this particular configuration here of the spring. So in this case, the forces on the spring balance out. So over here, if I just kind of redraw this down here, in this case, I only have two forces. The first force is the restoring force of the spring. So in this direction, I have my F sub s, which would just be K times delta L if it's at equilibrium. And then the other force that I have is this force from gravity, which is just minus m times g. Okay, so since these forces are balanced out within this configuration, I know that these forces have to sum to 0. So forces are balanced implies that F sub s plus F sub g has to be 0. Okay, so in particular, f of s in this case gives me that this F sub s has to be equal to mg. Okay, so from here, I can do this replacement up here and replace this with mg. So net, I have that my F sub s in the full configuration over here is simply going to be equal to mg minus ky. Okay, so if I just kind of box all this in, this is what I have for deriving this F sub s force acting on the spring. Okay, so it has to have this form where I've gotten rid of that dependence on that kind of nasty delta L where I really couldn't do anything with it as it stood. Okay, so now we've covered gravity and we've covered the force of stretching and compressing of the string. Is there anything else that can happen here? Well, in general, if I have a moving object, kind of tying into your assignment 2, I could have some type of air resistance or some type of dampening force fighting the act of motion. So in addition to the 2 points above, we have this dampening force. So the natural question to ask is, well, if we have this dampening force, what is it equal to? Well, here we're just going to give you this, but it's natural to think that, hey, if I have some kind of resistance to motion, then it should be at least proportional to the velocity, right? So if I'm going faster, I have more of a dampening force that's acting to try to act to slow me down. So here I can just call this minus c y prime, where this is my derivative of the position with respect to time. Okay, so y minus c, well, it turns out that it's convenient to have a negative here when we go to talk about the different types of dampening that we can have. Okay, so basically this acts to slow down the object from traveling at any particular speed. So if you want to think of it in kind of a natural way, if I have some spring moving through air, so I have a little blocks like this, this moving back and forth through air, then as it wants to move forward, there's these little air particles here that it has to push out of the way to go around it like this, right? And the act of it pushing around there is going to induce a force in this direction that I call F sub d that slows down the motion, okay? So I'm going to erase this from this copy here just because, yeah. Okay, so a slightly kind of cleaner version here. You just have to fight that motion. Okay, and this, again, is an assumption, but it's an assumption that ends up working. Okay, so are there any other forces that we could have here? Well, yes, we could have an external force or multiple other external forces, and these could be anything from wind blowing or anything like that. So here we're just going to denote these extra forces by a capital F. And we know these things can be here, and depending on the problem, you may or may not have them, but we do need to consider them in our model. Okay, so what have we done so far? So if I zoom out and kind of look at the big picture, so we started with F is equal to ma. We knew m was the second derivative here, and a was the second derivative here, and m was just the mass of the ball, or whatever's attached to the spring. So in addition to this, we have this capital F, which we've broken down into, at least within this context, force due to gravity, force due to the string wanting to go back to its equilibrium force, and a dampening force and potential external forces. So if we kind of zoom in and combine all these together, what does my F is equal to ma now give me? Well, I'll just write it as ma is equal to F. This thing gives me the following. So I have my double prime is equal to, well, this is just going to be the sum of the forces. So here I have my force of gravity, which I will just simply denote as F sub g, plus, in addition to this, I have my dampening force, so I'll just call this F sub d. I have the force due to the spring trying to go back to its equilibrium position. And finally, I have these external forces, which they really depend on the problem, so I'll just leave it as F. Okay, so from here, if I add these together, the force of gravity, that's just minus mg. The force of dampening, well, that's just going to be a minus cy prime. The force of the spring trying to restore itself, that had two components, right? It had the first component, a mg, from the kind of equilibrium length and the balance that we had there, and then we had the second term, this minus mk, so oops, minus ky, I meant to say, and finally we have this force here. So if I kind of clean this up, you can notice this cancels with this to simply get that this is minus cy prime minus ky plus f. Okay. This is not written in the standard form that we usually write our differential equations in when we go to solve them. So we can clean this up, and once we do that, the equation for a spring would simply be this term here is equal to f. Okay, so this is the governing equation for a spring mass system. And while this, you may be asking yourself, like, why do we go through all these details of a spring? I'm an electrical engineer. Do I really care about spring oscillatory systems like this? And the answer to that is yes. There are many other models. For instance, if you want a circuit with an inductor in it, which I hope to be able to cover that, I think we will have enough time to do that, that end up with similar derivations using not the same laws, but very similar physics laws to drive a very similar equation down here. So being able to understand how you could apply F is equal to ma to get these type of models is something that's a little bit beyond the scope of the class. I'm not going to explicitly ask you to drive something like this, but you should sit through and understand how this works for at least one of these problems, because it ultimately will allow you to be able to derive other systems of equations to talk about other systems similar but not identical to this. Okay, for instance, one such similar model that kind of has a very similar derivation is up here with this wave equation problem. What you're really doing with this wave equation to derive it is you're saying, oh, I have this spring like this, I have an equilibrium position here, and I'm going to apply Hooke's law on each of these little intervals here and tie them together. If you do that on, say, a discretized system where you have little blobs of string like this, and you apply it to each one of these blobs, and apply f is equal to ma, if you then take the limit, you end up getting this equation here. So I'm not going to force you to go through the derivation of the wave equation, but now that you've seen Hooke's law, you could, say, go to Wikipedia or something like that, and you would now have the ability to understand this derivation with a few little caveats, a few details that are slightly different. Okay, so the purpose of going through this and the whole reason why I made you sit through this is so that you'd be able to understand other derivations or potentially be able to drive some of these equations on your own within different contexts. Okay, so now what are we going to talk about? Well, we now have a shiny new model for physically modeling these types of situations with springs. So the natural first thing to do is to examine some of these models and try to solve for the motion of the oscillator, right? And just looking at this equation, m is going to be constant. C, we can assume it's constant, and kind of a broader context, it won't necessarily be constant. And this k, we know it's a constant under the assumption that Hooke's law still holds. And this forcing term, well, we don't necessarily know what it'll be, but we do know how to solve these second order linear difference equations with constant coefficients for a variety of forcing terms. So let's just kind of examine some various types of motions that we could get. And we're going to do this by start examining simple harmonic motion. So that is to say motion where there is no dampening and where there is no forcing term. So if we're going to be explicit here, we're really just saying motion with c is equal to f is equal to 0. Okay? And here with f, I really mean to say f of t for all values of t is equal to 0. So let's look at one of the examples of the book and get started. Okay, so for this problem, we're told that an object stretches a spring 6 inches in equilibrium. And in part A, we want to set up an equation of motion and find its general solution. And then we'll discuss part B once we get to there. Okay, so what does it mean for this object to stretch a spring 6 inches in equilibrium? Well, let's first just draw a picture of this. Okay, so here I would have, so part A, here I would have my kind of default string that would look like this. And here, once I put this mass on it, which I'm not told what the mass is, but once I put on the mass, I would simply have something that looks like this with some mass m sitting here, and this distance from here to the end over here is what I'm going to call to be the 6 inches. Okay? So this is all I'm told in the problem is this little bit of information here, which naturally begs the question, how do I possibly go about trying to model this? Well, we know since this is a spring mass system that it's going to be modeled by this equation up here, and we're going to assume that for this case we have simple harmonic motion, namely that we're not damped and we don't have any forcing terms. Okay? So from here you'd really have to know it from the problem. Here the text has the intention of this being a system that is not dampened. So in this case we could simply say this equation, this y double prime plus ky is equal to 0. This is going to be my equation of motion. Okay, so that's all good and fair, but I haven't told you what m is, and you don't know what k is. So how can you even go about trying to solve this? Well, this is where it's important to know the theory of the idea as opposed to just, here's the equation, do something with it. If I rewrite this equation like this, so it's the same as what I had before, I can use the way that I kind of went about this derivation to be able to find what k divided by m is, despite the fact that I don't know what k is on its own, and I don't know what m is on its own. So how? How can I do this? Well, if you go back up here in my derivation, I found this kind of natural balances of forces in this situation here, right? So when I just attach a mass and let it go to its new equilibrium state, I found that my k delta L was simply equal to minus mg. Okay, or I misspoke there, positive mg. It's the sum of these things being 0 that I need. Okay, so I know k delta L is equal to mg, so even though I don't know what delta L is, even though I don't know what k is or m is, I can use this one equation to solve for k divided by m. Okay, so let's see how we do that down here. Okay, so here I would note that mg is simply equal to my k times delta L, okay? And here I know what g is, g is gravity, and I know what delta L is because it was told to me up here, 6 inches, right? So from here, this allows me to solve for k divided by m. All I would simply have to do is divide this by m and divide this by delta L. So I get this thing is simply going to be equal to g divided by delta L. Okay, so knowing derivations are important precisely for the ability to solve questions like this. Okay, so from here, I need to kind of plug in values here, and how do I go about doing that? Well, I know what gravity is, both in meters per second and feet per second, but L was simply given to me in inches. So here what I have to do is I have to convert things to be in the same units. So be very cautious of doing that for these type questions. If you don't convert to the right units, you will get the wrong answer. So I want this to be 32 feet per second squared, all divided by L in the same units. So L is 6 inches, so that would be 1 feet in freedom units. So here if I chase this out, this whole thing has units of 64, 1 over second squared. Okay, so now I'm not going to knock you off if you don't put, or mark you off if you don't put the units here, but it can be very useful to verify you're doing everything correctly. And at the end of the problem, if I ask you for some information out of this model, I do want units attached to the final product, but in the middle, you can skip them if you want to. Okay, so now at this point, I know what k divided by m is, so here I can simplify my model just by simply saying something like thus. My equations of motion, so EOM, would simply be y double prime plus 64y is equal to 0. Okay, and we actually know how to solve these equations of this form pretty readily, so I'm going to not waste your time here. You should know how to solve this, but find the characteristic equation, find the roots of that. We can get that the solution is simply y sub s is equal to c1 cosine of 8t, and again here 8 just because 8 to the square root is 64, plus c2 sine of 8t. Okay, so we now have a solution to this harmonic motion within this context, and now we want to go to part B where we actually solve an initial value problem. So here we want to find the displacement of the object for t is greater than 0 if it is initially displaced by this 18 inches above equilibrium and it has a downward velocity of 3 feet per second. So basically what we need to do for part B is we need to turn this information that we just read into an initial value problem. So how do we get initial values from here? Well, the displacement tells me what y will be initially. So here this is saying initially I'm displaced 18 inches above it, so I can say initially y of 0 is simply going to be my 18 inches divided by 12 to convert it to feet. So in this case, this will simply be 1.5. Okay, so again, I need to convert this to feet because everything over here with this k over m had units of, well, so k had units in terms of feet. So the units of y here also have to be in feet, okay? So here you don't have to say it explicitly, or I won't knock off points if you don't say it, but you need to know that this is feet because in the end we might want something in terms of the actual units. Okay, so beyond here we need to know what the initial velocity is. Well, here I'm told that I have a initial downward velocity of 3 feet per second. So this means that initially the velocity is decreasing. So this is going to be minus 3 and feet per second, which is the units of velocity. So I'm good here. Okay, so now that I have this, the next thing that I want to do is simply apply these initial conditions to figure out what the solution has to be. So that's pretty trivial to do here. So let's just chase it out here. So if I plug in 0, my cosine term is non-zero. So this implies that my C1 has to be 1.5, again, units of feet. Here, if I take the derivative of my sine will give me a cosine with an 8 out front. So from here, this will imply that 8 times C2 has to be minus 3. Thus, I have simply that C2 is equal to minus 3 over 8. So if I put this together, my solution, y sub s, is simply going to be my C1, so 1.5, cosine of 8 times t, plus my negative 3/8, so I'll just leave it as a minus 3 over 8 times my sine of 8t. Okay, and this is my final equation for the displacement of the spring with respect to time. Technically, it even works for negative time going the other way, but generally speaking, we usually don't talk about time going in the negative direction, so we kind of suppress that information here. Okay, so now that we found a solution to this, let's take a step back and see if we can better understand this solution, right? Here we have kind of a sum of sines and cosines that could be something that's kind of complex, but it turns out that it actually isn't. So let's just think physically of what these solutions should look like. So if this is time going increasing this way and this is y, if I start at an initial displacement up here with, say, a velocity of 0, just for whatever reason, we would think that the speed should kind of increase as we get closer and closer here. So the slope of this line should get sharper. And then once we cross here, it should start slowing down because the force is acting to, well, fight the opposite direction, right? And we would just think if there's no kind of nonlinear extra forcing terms here, the forces acting in one direction should be equal to the forces going the other direction. So physically, what I'm really trying to get to here is that this coefficient k is constant, right? So this f of s is kind of symmetric across that equilibrium point, and so are the rest of the forces other than the gravity force, this negative mg. That wasn't symmetric across the equilibrium point, but it cancels with this mg. Okay, so we should expect that we should have some symmetry, if I just try to draw this out further, across this y is equal to whatever the equilibrium was. So in this case, we could just call it 0 if you put the coordinate system sitting there, which is what we're really doing over here. So just kind of from this physical argument for there's no reason, there's no force to make this asymmetric, we should expect that our solution itself should have this nice symmetry. Thus, we should expect, like we expect, the solution to be periodic. And in fact, if you actually plot this function here analytically, you do get that this does look periodic. So that begs the question, if it is periodic, I should be able to write it as maybe in terms of sine or cosine or some other periodic function, not necessarily those two. So is it possible, and if so, how can we write this y sub s as some periodic function? Well, let's look into that. And the way that we're going to look into this is by first examining the difference equation that we had up here, but without these numbers in here, just to have it in its most general framework. So what we're going to do is we thus examine the original differential equation, which was explicitly m y double prime plus my ky is equal to 0. Okay, so we know this thing is equivalent to the expression when I divide by m, assuming the mass is non-zero, which, yeah, if it's non-zero, then you don't really have a problem here. So we can do this thing here is equal to 0. Okay, so we noticed before this thing was positive, and in general, this thing will need to be positive if I want this to be a restoring force. So I can call this thing omega naught squared. Okay, so why rename it? Well, it turns out that over here, when I did this stuff, I end up taking the square root of whatever number is here. So if this thing is something squared, when I square root it, I simply get omega, and that's convenient to have. Okay, so I'm just going to call this thing omega naught squared, and again, it's because k has to be positive for this to be a restoring force. So again, this goes back to the derivation. If k were to be negative over here, what would that tell me? Well, that would say that if I go more negative, then the force is kind of pushing it apart. So it's really kind of the opposite of a spring. It's a spring where if you go out of equilibrium, it goes further out of equilibrium out to infinity. So that's not a thing, at least within this context it isn't. So yeah, that's why we do this. Okay, so if we solve this, which we know readily how to solve, then I can simply get a sum of sines and cosines like this. So this solution here. Okay, so now that we have this, we still have the same problem that we had in the previous case, other than things are kind of more general. I don't know what C1 and C2 are, but I know they're some numbers. And I don't know what omega naught is, but I know it would be some number. Well, in particular, it'd be the square root of this thing. So from here, how can I simplify this to be a single periodic function? It turns out that I can actually turn this into a cosine, so let's see how we can do this. Well, first, what we're going to do is we're going to make a coordinate transformation. Okay, so if we're introducing a coordinate transform, what coordinate transform are we introducing here? Well, what we're going to do is we're going to transform from our coordinates that we currently have using this C1 and this C2. So we're going to have a coordinate transform from C1, C2 to a new system where I have two new coordinate variables called R and phi. So from here, I want this transform here, and I'll just write it out so you don't have to see it. Okay, so how is this coordinate transform going to work, and why am I even doing this? Well, the why is if I define things properly, I can end up rewriting this thing as a single cosine term with period omega naught, right? This function here would be a periodic function with omega naught, so you might think I could do that. Turns out that I can. Okay, so that's the why, but the next question is the what. What transform am I going to have here? Well, R, I'm just going to explicitly define to be the square root of C1 squared plus C2 squared. Okay, so notice here, if I were to take the norm of this thing here, I would end up with this term squared plus this term squared, and the sine and cosine terms via identities cancel out, so I end up simply getting the square root of these two things. So R is simply the length or the total displacement of this thing here. Okay, so that's a pretty natural quantity to define. And next, I'm going to define theta by simply defining C1 to be equal to this R cosine of phi. So C1 is equal to R cosine of phi. So this is really a defining quantity for phi, and it actually turns out that with this definition and this definition of R, you can do a little bit of work and you can explicitly prove that this would imply that C2 has to be equal to R sine of phi. And I actually misspoke here with the way that I put my coefficients. This one, for things to work out the way that we want, needs to be C2, and this one needs to be C1. The other way does give you a well-defined coordinate transform. It just doesn't do what we want this to do here. Okay, so here you can kind of tell if I give you a value of C1 and C2, you could compute this to find R, and then you could use either one of these to find phi, and it turns out that they'll both get the same expression. And alternatively, if I give you R and phi, you could put these together and find what C1 and C2 are just from these two bottom expressions here. Okay, so this is a coordinate transform, and I can invert back and forth given that things are well defined. Here we just need things to be real numbers for this to be well defined. Okay, so now that I have this transform that I've defined, let's see what actually happens. Well, here, this is going to give me an equals, and this is really coming from this definition here. If I plug in C1, I'm simply going to get R sine of phi times sine of omega t. So explicitly writing it out, I get that term here. And on the other side, I'm going to simply get my C2 will be replaced by this R cosine of phi. So I'll get a R cosine of phi, and that'll be multiplied by cosine of omega t, or omega naught t. So again, this is a choice of how to do this. You could do it differently. It just doesn't work out as well. So let me clean this up real quick. And there we go. So now what we can do is we can factor out a factor of r out of both of these terms. And then we can notice that we'd simply have sine of phi times sine of omega t plus this cosine of phi times cosine of omega t. And it turns out that there's a nice identity, which I'm not going to prove here. It's not too bad to prove. So if you wanted a good exercise, you could prove it, but I'm not going to test you on this identity. But using a trig identity, we can simply rewrite this whole thing as r times the single cos here. So if I tie back into my previous picture, the r will tell me how far I deviate out here. So let's just draw this in. This thing here is going to tell me my capital R using that information down below. And here, this theta naught, that is going to tell me my period of this. So here, this goes from here all the way over to here. So this length would be my omega naught. Okay, and what is this phi? Well, phi turns out that it's just going to be something that tweaks my phase by a constant, and generally speaking, you call it the phase or the phase angle. So there's infinitely many values of phi that would satisfy this transform, right? Because there's infinitely many values that I can plug into cosine to get the same number coming out, and yeah. And then this omega naught, we usually call it the frequency of motion or the natural frequency. And the R, we usually call it the amplitude of the wave. So I'll just, for completion of the notes, I will put all those definitions there, but they're also in your text. Okay, so I think all of us will agree that this boxed termed here is much nicer to work with than something that looks like this. Okay, so if I don't ask you to put a solution in this form, then you don't have to. But if I do ask you, obviously you would have to at that point. Okay, so we're going to end this lecture by looking at one more example from the text, example 6.1.2. So here, basically, we found the solution previously to be this. Find the frequency, period, amplitude, and phase angle of the motion. And here, let's just jump into it. So if I have something like this, if I want to find this data, I really just need to use this coordinate transform information here. So if I want to find the amplitude would just be this r here. So I could simply say the amplitude is, and this will simply be r is equal to the square root of my c1 plus c2, or c1 squared plus c2 squared. So 3 over 2 quantity squared plus 3 over 8 quantity squared. And here I'm dropping the negative under the square root just because it doesn't make a difference here. So here, if you just do some standard arithmetic, you can simplify this out to be 3 over 8 times the square root of 17. Okay, so that's how to find the amplitude here. So now if I want to find the frequency of this is kind of the easy bit. So I'm just going to say the frequency is, now this is just going to be my omega that's sitting here. So the frequency would be omega naught is equal to 8. Okay, that one's pretty trivial to grab. Okay, and from here, if I have the frequency, I can find the period. So I can say, thus, is, and here the period will simply always be usually denoted by t. You don't need to use the symbol if you don't want to, but it'll simply be 2 pi divided by the frequency. Okay, so in this case, just pi over 4. Okay, and here I'm kind of assuming that you know how to convert from frequencies to periods. Basically, if I give you something that looks like sine of 8 pi, or 8t and ask you what its period is, it's always going to be 2 pi divided by whatever the scalar is. Okay, so if you're not familiar with that, you should be now. So yeah. And finally, we want to determine the phase angle. So we have options for how to compute the phase angle. I could use this term here. I could use this term here, or I could put them together and use tangent. So let's just use the tangent one just to show you something that's different from the book. So here I could simply say to find the phase angle, we note, and what are we going to note? Well, if I take my C1 and divide that by my C2, so in this case, those two numbers here, this would simply be equal to what? Well, it's going to be R sine of phi divided by R cosine of phi, and this is just tangent of phi. So from here, if you just pick any of your kind of standard angles for tangent, this gives you another way that you can solve for here. So in this case, what is my C1 and C2? Well, C1 is always the coefficient in front of my tangent, so that's 3/8, and here my C2 would be 3/2. So if I put these together, I get simply that this implies my tangent of phi would be equal to my -3/8 divided by 3/2. If you do the algebra to simplify this out, that simply becomes a -1/4. So I lost my little marker there, but -1/4. And here, if you solve this for phi, basically plugging it into a calculator to get it from here, you would simply get that phi is equal to 0.245 with a negative in front of it there. Okay, so yeah, that's one way to do it. You could use the ways in the text where you just basically solve one of these other expressions instead. It's really up to you, but that's how to compute all of this stuff here. So with all of this in mind, you can very clearly see how the spring will be oscillating within these cases. And it's a lot nicer than working with the expression that we had over here. Okay, so if I just want to put all of this together for a nice ending point for this question, I can thus say with this y up here, I could rewrite the whole thing as y is simply going to be equal to, well, r was simply this 8/3 squared is 17, or 3/8, so I'll have this term here. And then I'm simply going to have that times cosine of my omega naught, so 8t, plus my phase, so minus, in this case, 0.245. Of course, you can add extra decimal points, or if you want it to be exact, you can leave it as tangent inverse. But this is what my solution roughly looks like, where roughly is this approximation that I put here to compute phi. Okay, so for this section, your assigned reading is to read pages 268 to 273, and to look at example 6.1.3. Okay, so this is basically what we covered here in the second half, talking about the simple harmonic motion stuff. They give a slightly different derivation, so if you find it more useful or kind of useful to see a different way of approaching things, albeit quite similar, you can check that out. And then I want you to look at all of the, well, for practice problems, look at all of the unforced questions. Again, you don't have to look at all of them, but that's just what's recommended here. And finally, for our meme, we have this guy here, harmonic oscillators everywhere. So this is actually not an understatement here. So we talked about the spring system being a harmonic oscillator, but another example is if you take, say, a pendulum that has kind of its normal state here, this is actually a harmonic oscillator. Further, in like a lot of watches, they will have a quartz crystal, so like quartz watches. So there you'll have like a little crystal here, and you kind of hit the crystal with the hammer, and then the crystal oscillates at a frequency. That's a harmonic oscillator. Further, atoms themselves are actually harmonic oscillators, and they have fundamental frequencies that are found by quite similar setups here. So here you have a little atom, here you can have your little electrons, orbitals going around it. Those orbitals are actually modeled quite well by harmonic oscillations. Okay, so this is a very deep topic here, and we will explore it more in the next 3 lectures.